The ground beneath Mount Semeru did not just shake on November 19th, it split open and screamed. For 72 hours, Indonesia's most relentless volcano has been hurling pyroclastic flows down its slopes at 400 miles per hour, turning peaceful farming villages into evacuation zones and clear skies into ash-filled nightmares. But what scientists are discovering in the seismic data, the satellite imagery, and the volcanic debris is not just about this eruption. It is about what lies hidden beneath Java's most populated island. A network of geological forces that could reshape our understanding of how volcanoes communicate with each other beneath the surface, and whether this volcanic awakening is just the beginning of something far more catastrophic. At exactly 2:13 p.m. local time on November 19, 2025, Mount Semeru's summit crater did not just erupt. It exploded with a force that sent ash columns 12 miles into the atmosphere. Within minutes, superheated avalanches of gas, ash, and volcanic rock were racing down the mountainside at temperatures exceeding 1,800 degrees Fahrenheit. Sari Wulandari was hanging laundry in her backyard in Supaturang village when the mountain roared to life. She recalls that the sound was like a jet engine mixed with thunder that never stopped. Then the sky went dark, and they knew they had maybe minutes to run. By 2:45 p.m., pyroclastic density currents, walls of superheated volcanic material moving faster than hurricane winds, had traveled over 8 miles down Semeru's southeastern flanks. The Besuk Kobokan River channel, which normally carried crystal-clear mountain water to rice paddies below, became a highway for destruction, moving at 200 miles per hour. But it wasn't the visible devastation that sent chills through Indonesia's Volcano Monitoring Center in Bandung. It was what their seismic instruments were detecting beneath the surface. In the first 24 hours following the eruption, monitoring stations scattered around Semeru recorded 118 distinct eruption earthquakes, each one representing magma movement deep underground. The frequency was unprecedented. Most concerning was the pattern. Rather than decreasing as pressure was released, the seismic activity was intensifying. Dr. Hendra Gunawan, head of volcano monitoring for Indonesia's Geological Agency, studied the real-time data with growing unease. He reported to emergency coordinators that the seismic signature suggests magma movement from much deeper chambers than previously detected at Semeru. He said scientists were seeing source depths of 15 to 20 kilometers, far below the typical 3 to 5 kilometer range. The implications were staggering. Shallow magma movement indicates a localized eruption. Deep magma movement suggests something far more extensive, potentially involving the massive underground system that feeds multiple volcanoes across Java's volcanic arc. As pyroclastic flows carved new paths down the southeastern flanks, GPS satellites measured something that made volcanologists around the world take notice. Ground deformation wasn't confined to Semeru's immediate base. The entire mountain was shifting, with subtle millimeter-scale movements detected across a 20-kilometer radius that indicated massive underground pressure changes. These weren't just the typical inflation patterns seen before eruptions. The ground was moving in complex, interconnected ways that suggested Semeru's magma system was responding to forces originating far below the visible mountain. But that seismic activity was only revealing the surface of a much deeper geological reality that scientists were beginning to understand. Mount Semeru does not exist in geological isolation. It sits directly above one of Earth's most complex and dangerous tectonic intersections, where the Indo-Australian, Eurasian, and Philippine sea plates collide in a violent, ongoing process that has shaped Indonesia's volcanic landscape for millions of years. Every year, the ocean floor is forced beneath Java Island at a rate of 2.6 inches through a process called subduction. As the oceanic plate descends into Earth's mantle, it heats up, melts, and creates magma that rises through fractures in the overlying crust. This process has built the chain of over 130 active volcanoes that stretches across the Indonesian archipelago like a necklace of geological time bombs. Recent research using advanced seismic tomography, essentially creating three-dimensional X-rays of the underground structure, has revealed something that changes our understanding of how these volcanoes operate. They are not independent systems. They are connected through a vast network of magma chambers, fracture zones, and pressure release pathways. and these can influence each other across distances of hundreds of kilometers. Dr. Mirzam Abdurrahman from Bandung Institute of Technology has spent the last decade mapping these underground connections. He says that Java's volcanoes share plumbing systems in ways researchers never imagined. And when one major volcano erupts, it can affect magma pressure and movement throughout the entire volcanic arc. The evidence for this interconnection became undeniable following the November 19th eruption. Satellite interferometry from the European Space Agency Sentinel-1 radar detected ground displacement not just around Semeru's base, but along a corridor 60 kilometers long stretching toward Mount Bromo, another highly active volcano about 35 miles to the northwest. The displacement pattern suggests that Semeru's eruption created pressure waves through the underground magma system that reached neighboring volcanic centers. If this interpretation is correct, it means that major eruptions do not just release local pressure. They can redistribute stress throughout the entire regional network. Historical analysis supports this disturbing possibility. In 1815, when Mount Tambora erupted with the force of 1,000 atomic bombs, causing global climate cooling and crop failures worldwide, it was preceded by months of increased volcanic activity across the entire Sunda arc. Seismic records from that period show a clear pattern. Smaller eruptions at multiple volcanoes leading up to Tambora's catastrophic explosion. Similar patterns preceded the 1883 Krakatoa eruption, which killed over 36,000 people and was heard 3,000 miles away. The eruption from 1963 to 1964 of Mount Agung in Bali killed nearly 2,000 people and disrupted global air travel for months. The common thread in all these disasters was the same geological signature now appearing around Mount Semeru: deep seismic activity, ground deformation across wide areas, and changes in gas emissions from multiple volcanic centers simultaneously. What makes this current eruption particularly ominous is how closely it mirrors a recent disaster that geologists hoped would never repeat, but feared inevitably would. December 4th, 2021. The morning started like any other in the farming villages scattered around Mount Semeru's base. Rice paddies stretched in green terraces down the mountainsides. Children walked to school along paths their grandparents had used for decades. The mountain looked peaceful, almost benevolent, its summit often hidden by gentle clouds. But farmers in Cura Kobakan village had noticed something troubling in recent weeks. The basic Kobakan River, which flows directly from Semeru's base and provides irrigation water for thousands of acres of crops, had turned an unusual gray color. Fish were dying. The water carried a sulfur smell that lingered in the air for days. Local officials, when pressed by concerned residents, classified it as normal volcanic activity. Mount Semeru, after all, had been in nearly continuous low-level eruption since 1967. Gray water and sulfur smells were part of living in the shadow of an active volcano. They were catastrophically wrong. At 3:47 p.m. on December 4th, 2021, without any dramatic warning signs, Mount Semeru's crater suddenly collapsed, sending pyroclastic flows racing down the mountainside at 120 miles per hour. The superheated avalanche followed the basic Kobokan River channel like water flowing downhill. Except this water was 1,800-degree gas and rock, moving faster than anyone could run, drive, or escape. Suharyanto was working his rice fields when the flow hit Cura Kobokan. He told reporters weeks later from his hospital bed, his arms still wrapped in bandages from third-degree burns. He said he heard this sound like a freight train, but there are no trains here. He looked up and the sky went black, then orange, then everything was fire. The river we trusted our whole lives became a highway for death. The pyroclastic flow traveled 7 miles in under 10 minutes. Entire villages simply vanished under 15 feet of volcanic debris, their locations marked only by the tops of palm trees poking through gray volcanic sand. Houses that had stood for generations were swept away like paper in a flood. 51 people died that day. Over 10,000 were evacuated from their homes. Nearly 3,000 houses were destroyed. Schools, mosques, bridges, roads, all erased by the unstoppable force of volcanic fury, channeled through a riverbed that families had trusted for centuries. But the real tragedy wasn't just the eruption itself. It was how the geological warning signs had been building for months, growing stronger and more obvious, while authorities maintained that everything was normal. Increased seismic activity throughout November 2021. Ground deformation detected by satellite monitoring. Changes in gas emissions from the crater. Rising temperatures in hot springs around the mountain's base. All indicators that deeper magma chambers were becoming active, that pressure was building toward a critical threshold. The warning signs were there. They were documented. They were dismissed as routine volcanic activity until 15-foot-high pyroclastic flows turned villages into graveyards. In the aftermath, Indonesian authorities promised better early warning systems, expanded evacuation zones, and more aggressive monitoring of underground activity. They vowed that the communication failures and delayed responses that cost lives in 2021 would never happen again. But now, scientists examining data from the November 19, 2025 eruption are seeing those same geological signatures appearing again, except this time they are stronger, deeper, and more widespread than anything recorded before the 2021 disaster. The November 19th eruption forced over 1,000 people from their homes within hours. By November 21st, evacuation zones had been expanded to 8 kilometers from the crater, nearly double the standard distance for Semeru eruptions. The reason was not just the pyroclastic flows themselves. It was what the flows revealed about fundamental changes in Semeru's underground architecture, as volcanic debris carved new channels down the mountain. Thermal imaging satellites detected heat signatures extending far beyond the main crater. Multiple vents along the southeastern slope were showing elevated temperatures, suggesting that magma was not just rising through Semeru's primary conduit, it was finding new pathways to the surface through fracture systems that had not been active in recorded history. Indonesia's Volcano Observatory raised the alert to level 4, the highest possible classification, but their technical reports contained details that were deeply unsettling to volcanologists worldwide. Current seismic patterns indicate magma intrusion at depths not previously mapped, read one assessment. Deformation modeling suggests involvement of deep-seated magma chambers extending beyond the immediate volcanic edifice. In scientific terms, this meant that Semeru's eruption was being fed by magma sources much deeper and more extensive than any previous eruption in the mountain's recorded history. The implications were staggering. Dr. Cristianto, a government volcanologist monitoring the crisis, explained the significance during an emergency briefing. When we see shallow magma intrusion, we expect localized eruptions that follow predictable patterns. But deep magma intrusion, especially from previously unknown chambers, suggests we are dealing with a volcanic system we do not fully understand. The Besuk Kobokan drainage, the same river channel where 51 people died in 2021, was once again filling with volcanic debris. But this time, ground-penetrating radar surveys revealed void spaces beneath the riverbed, cavities and tunnel systems that could indicate magma movement through underground fracture networks extending for dozens of kilometers. If these fractures connect to other volcanic centers in the region, a large eruption at Semeru could potentially trigger sympathetic eruptions across Java's volcanic arc. With 150 million people living within range of active volcanoes, including major cities like Surabaya, Malang, and Yogyakarta, the stakes could not be higher. By November 21st, seismic monitoring stations were recording 42 eruption earthquakes every 6 hours, a rate of volcanic seismicity that indicated massive ongoing magma movement deep underground. More concerning, the earthquakes were getting deeper and more powerful, suggesting that the eruption was tapping into progressively larger magma reservoirs. Gas monitoring revealed another ominous trend. Sulfur dioxide emissions, which indicate magma degassing, had increased by 400% compared to pre-eruption levels. The gas composition also included unusual concentrations of hydrogen sulfide and carbon dioxide, signatures that suggest magma interaction with deep groundwater systems or previously sealed gas pockets. Weather patterns complicated the crisis further. Heavy rains on November 21st generated lahars, volcanic mud flows that raced down river channels at 50 miles per hour, carrying boulders the size of cars and enough debris to bury entire villages. These were not just surface water picking up loose ash. The lahars contained fresh volcanic material, indicating that ongoing eruptions were continuously feeding debris into the drainage systems. Local residents reported unusual phenomena that had not been observed during previous eruptions. Wells dried up suddenly. Hot springs changed temperature and color. Ground cracks appeared in rice paddies several miles from the mountain. Animals behaved strangely, with livestock refusing to graze in certain areas, and birds abandoning roosting sites they had used for years. These were not just anecdotal observations. They were surface manifestations of underground changes that could indicate the beginning of a volcanic crisis, unlike anything in Indonesia's recorded history. Every 12 hours, seismometers positioned around Mount Semeru detect new earthquake swarms emanating from depths of 15 to 25 kilometers below the surface. Every day, gas sensors measure increasing sulfur dioxide emissions that indicate massive ongoing magma degassing. Every satellite pass reveals continued ground deformation across an area now extending over 100 square kilometers. What scientists cannot predict is whether this represents the peak of Semeru's current eruptive cycle, or the opening phase of something far more catastrophic. Dr. Mirzam Abdurrahman, who has studied Indonesian volcanoes for over 2 decades, describes the current situation with unusual gravity. She says we are observing volcanic behavior that suggests fundamental structural changes in the deep magma system. Whether this leads to gradual pressure release over months or years, or catastrophic failure within days or weeks, depends on variables scientists are still trying to understand. The geological reality is both fascinating and terrifying. Java's volcanic arc has produced some of the most devastating eruptions in human history, events that changed global climate and reshaped entire regions. Tambora in 1815 caused the year without a summer across the northern hemisphere. Krakatoa in 1883 generated tsunamis that killed tens of thousands and was heard on the other side of the planet. Galunggung in 1822 ejected so much ash into the atmosphere that it created stunning red sunsets worldwide for months. Each of these catastrophic eruptions followed periods of increased volcanic activity remarkably similar to what is happening now across Java's volcanic region. Multiple volcanoes showed increased seismic activity. There was ground deformation across wide areas, changes in gas emissions and thermal patterns, and unusual behavior in groundwater and hot spring systems. Modern volcano monitoring gives us unprecedented data about these underground processes. Satellite interferometry can detect ground movements measured in millimeters. Seismic networks can pinpoint earthquake locations within meters. Gas sensors can identify minute changes in volcanic emissions that indicate magma movement at depths of 20 kilometers or more. But all this technological capability also reveals how much we still do not understand about volcanic systems. There may be deep magma chambers that could feed multiple volcanoes simultaneously, fault networks that could channel magma across vast distances, and pressure release mechanisms that could either prevent catastrophic eruptions or make them inevitable. Current research suggests that major volcanic eruptions do not occur in isolation. They are typically the result of complex interactions between regional tectonic stresses, deep magma reservoir dynamics, and surface geological conditions that can influence each other across hundreds of kilometers. The question facing Indonesian authorities is not whether Mount Semeru will continue erupting. It has been in nearly continuous eruption for over 50 years. The question is whether the current activity represents a new phase of volcanic behavior that could involve much larger magma reservoirs and potentially trigger eruptions at neighboring volcanic centers. Evacuation planning now extends beyond the immediate 8-kilometer danger zone around Mount Semeru. Emergency managers are developing contingency plans for scenarios involving multiple simultaneous eruptions across the Java volcanic arc, situations that would require evacuating millions of people from one of the world's most densely populated regions. Scientific monitoring continues around the clock. International volcano observatories are sharing real-time data and analysis. Research teams are deploying additional instruments to measure ground deformation, gas emissions, and seismic activity with ever greater precision. But beneath Java's verdant landscape, forces beyond human control or complete understanding continue their ancient, unstoppable work. Magma rises through fracture systems older than human civilization. Tectonic plates continue their inexorable collision, building pressure that must eventually be released. Mount Semeru continues to simmer, its deep underground systems following geological processes that operate on timescales far longer than human memory, yet that can explode into destructive fury with devastating suddenness. The evacuation centers around Mount Semeru house over 1,000 displaced residents who do not know if they will ever return to their homes. Farmers who have worked the same fields for generations watch from a distance as ash continues to fall on their rice paddies. Children attend makeshift schools and community centers, their normal classrooms buried under volcanic debris or located within exclusion zones that may remain off-limits for months. Sari Wulandari, the woman who was hanging laundry when Semeru exploded, now lives in a temporary shelter 15 kilometers from her village. Every night we hear the mountain rumbling, she says. Every morning we wake up wondering if today will be the day we can go home, or the day we learn we can never go home. These human stories play out against the backdrop of geological processes that operate according to laws of physics, not human timelines or emotional needs. Volcanic eruptions follow the mathematics of pressure gradients and magma density, not school schedules or harvest seasons. The underground forces reshaping Java's volcanic landscape respond to tectonic stresses that have been building for millions of years, not the immediate needs of farming communities or evacuation planners. Yet this intersection between geological time and human time creates profound questions about how societies should adapt to living with active volcanoes. Indonesia hosts nearly 130 active volcanoes because the same tectonic processes that create devastating eruptions also create incredibly fertile soils that support agriculture. The volcanic ash that can kill also enriches the earth in ways that allow Java to support one of the world's highest population densities. Emergency planners face impossible choices. Permanent evacuation of high-risk areas would displace millions of people whose livelihoods depend on volcanic soils. But allowing continued habitation of dangerous zones virtually guarantees future casualties when the next major eruption occurs. Not if, but when. The Mount Semeru crisis exemplifies this dilemma. The villages most at risk from pyroclastic flows are also the communities most dependent on agriculture, made possible by centuries of volcanic activity. The river channels that carry deadly volcanic flows during eruptions are the same waterways that irrigate the rice paddies that feed these communities during normal times. Mount Semeru continues to simmer. The exclusion zones remain in effect. Scientists continue monitoring underground activity that could indicate either gradual pressure release or catastrophic escalation. And beneath Java's deceptively peaceful landscape, the ancient conversation between tectonic plates continues, a geological dialogue that shapes the surface world through forces beyond human control, operating on timescales that dwarf human experience, yet capable of changing human lives in an instant.